Okay, so combinational circuits. So we talked last time about breaking down entities and architectures in VHDL, and then based on building up these fundamental gates, we can build up larger blocks in order to build combinational circuits. So last time we were talking about decomposing the function, and then any block not decomposed is called a primitive block. So we were building up AND gates, OR gates, NAND gates, NOR gates, etc., and doing all the testing for being able to ensure that if you get an unknown value, which is a U or a Z or any of the other values that are not a 0 or a 1, please sit down, thank you. Then what you want to do is you want to make sure that if we could properly test it, so that way, for example, we had the OR gate last class. That's a test bench. So we had this AND gate where if it was 1, it propagated the 1 value after 5 nanoseconds. And if it's 0 and these values, this indicates it's correct. But what happens if we have this else condition down here? This means, if you remember from the values of what were the topical guide objective about the, past it. Yeah, here we go. So you have all these different character values, not just zeros or ones. Ideally, that's what you get. But what happens if you get uninitialized or strong values? So X is a strong driver, meaning that we're getting a strong signal, but it's not. It's somewhere in between the 0 or 1 where we can't differentiate between those. Whereas if you get a weak, it's kind of a weaker signal, but you still can't differentiate. So this L and this H is kind of it's getting toward the 0 or 1, but it's not quite up to where we need it to be in order to say it properly represents a value. And so by properly testing the primitive blocks at the lowest level, we need to, I'll get to your question in a second. We ensure that we've properly tested, so that way when you're building the blocks, these larger blocks on top of your primitive blocks, you can ensure that the things that you're putting together are actually properly working. Thomas, what's your question?
When would you actually get that weak job signal?
Oh, so let's say you get some sort of issue where prior to your design, something's not properly designed. Say you do some VHDL and you screw up some wires and you don't tie the wires properly, and then you're just being constantly. We're going to be going a little into fan in and fan out, actually a little later today in class. But the idea is what happens if you have one circuit output, but the idea with fan out is you have a number of different wires driving it. So at one point, there's only so much that the one circuit can drive with the proper voltage and the current. So the result is the amount of current that you're actually driving to the other subsequent circuits comes down. So what happens if you're actually getting uninitialized values? There's possibly you designed this circuit correctly, you designed this circuit correctly, but you haven't properly designed the buses to get all the information to those circuits. So I kind of gone over this very simple example of A and B or C, and we're going to use a signal wire within the VHDL to indicate the connections between the AND gate and the OR gate. So we're going to have 3 inputs. So remember from our entity, we're going to have input A, input B, input C, standard logic, and then we're going to have an output signal F. So what we want to do is, since now that we have these 2 components within the VHDL architecture, we can use these to have code reuse. And so what's going to happen here is we have this, if gate 1 and gate, and it's called port map. This is the proper coding. So we have A is mapped to input 1. So what's happening here, let me go down just a little further so that way the people top in the back can see. So you have 3 inputs that we've designated in the component. Input 1, input 2, and input 3. Within the entity. And within from the entity, we have to map them to the components, right? So we have 2 components. We have an AND gate and an OR gate. So we map input 1 to A. So what it means is the component AND has value A, that we map input 1 to, right? Then we map B to input 2. So those component map to the value we're getting from the entity, right? Does that make sense? And so it's left to right. That's the notation. And then F1 is what we have from the entity to wire. Well, wire is a signal that we're using to connect the output from the AND gate to the next component, which is the OR gate. So we're going to have A and B. That wire represents the in-between output. And then we're going to have another input, which is input 3, going to the OR gate. As you can see, X is in the component is mapped to wire. So we have them connected now. So to answer your question, what happens if you map the wrong wire? If you do this, let's say we have 2 wires, we instantiate 2 wires. But we want wire 1 to connect, but for some reason, due to bad code, we have wire 2 written here. It will compile, it will go onto the board, and you'll get an uninitiated or unknown value because it's just taking something from nothing. So that's to answer your question, little brother. Yes?
What if wires connect to a Y?
What if R is connected to what?
The wire is connected to a Y.
That's fine, as long you can. OR gates are going to be logically, yes.
Okay.
It's going to be, they're logically equivalent circuits, so that's fine. I just did it this way for the example. And for the drawing that I have here, so you have the 2 entities we've created earlier with the AND gate and the OR gate. And then if you're building entities with previously created Vhdl, what you have here is you have an entity which is AND, A and B or C, and the way it looks physically is port 1, input 1 and input 2. So if you're building the entity, we have entity, combinational circuit, port, input 1, STD logic, input 2, STD logic, input 3, STD logic, and then port output is out STD logic. From there, you have to import previously made components. So here it's component and component OR, and then we also create the wire signal to connect them in between. So now we're actually creating the physical hardware layout using this hardware description language. And so the ports within that's where we do the port mapping within the code. And then you have, one important thing I should note right here, you have this output, so you have OR gates here, you have to make sure that you map the final output to the actual output of the overall higher level entity. So to look at this code, we have now, this is the VHDL code for this, which I've called combinational circuit, COMB circuit. So you have ports. So entity combinational circuit is port input 1, input 2, input 3 is in standard logic. Output is out standard logic. Now we get to the architecture. Since we're using 2 primitives, you have to include the components. So what we've done previously is we have the AND gates and the OR gates created, right? And then we use component AND gate is ABF1, and component OR gate is Y2F2, and component. And then we create the wire signal. So this is how we actually instantiate the wire. Signal wire is STD logic. I'm sorry, a signal wire colon STD underscore logic. Now sometimes you can go equals 0. Here if you want to instantiate as a 0, sometimes you do that. Sometimes you don't want to do that because if we, in this case, we have the wire in between A and B. So let's say we start out with our test bench where we have 1 and 1, right? And we have a value of 0. So we want our first change to go to a 1, right? From that output. But what's going to happen is if you have a 0 there, and you have a 0 there, so the circuit's going to be 1, 1, 0. A is 1, B is 1, C is 0. It should propagate the value 1 to the OR gate, at which point it will 1 or 0 will give you 1 on the output. But if you initialize this as 0, it'll actually have a 0 going out first because the actual answer is 0 until you change it. So that'd be an instance where you just want to leave the wire as is, which is how it's going to work. If you actually start up a circuit, the power is off. Yeah, so it's going to be actually off. Does somebody have a question? Okay.
And you can just use WA for input 3 for continuity.
Yes. Oh yeah, they have to match.
Well, sure.
That's a good question. That's a really good question. So A, B. So to address this here, I'll write it so you can. So the A here matches this A for the component. B matches the B, and F1 matches F1 here. X is Y is here, and F2 matches here. So it's going to match component here on the left maps to what's actually in the current entity. So input 1 comes from the entity we instantiated earlier, input 2, and then wire, and then input 3. And so if you had done X, input 3, Y is to wire, that will work too, provided that you design your OR gate properly. And then you mount F2 to the output. Does that answer your question? Okay, good. So last class, we went over an example of the difference between signals and variables. So signals are used to connect the design components and must carry the information between current statements of the design. Whereas variables are used within the process to compute certain values. So let's say you have two components. You want to use signals because now you're connecting actual physical implementations. Whereas variables, you can use this. If you have A and B connects to variable B1, and then you can use B1 to calculate the result of OR C. So B1 or C, if you want to do it that way. And if you remember from last class, one of the advantages of breaking down the code instead of just going A and B or C is when you get significantly larger circuits, breaking them down using signals and variables reduces that area, the bloat, the area overhead. You guys remember that? Okay. And so I showed the example in class of this code segment where we had a variable, and I actually had multiple instances. Like the code that I had also had a entity where I built up using they had A and B XOR C, so I'd use that to actually represent it using signals. And then I just used this process here. So this is the signal, and this is the variable. So this is, what it looks like is the exact same code, right? But what ended up happening is this calculates it immediately without any delay. And this inserts delay because of the fact that we have the difference is the signal is actually a representation of physical calculation, whereas variable is just like this is what it is. And so when you're simulating it, you have the signal immediately. And then in the actual lecture that I did last class, I had some code where we actually used two components, AND gate and an XOR gate, where I had coded 5 nanoseconds of delay into both of them. And do you guys remember what happened? What was the error that happened? Yeah, we had the little quick pulses. And the reason why is because we had the 2 inputs going to the AND gate, but we were already propagating the 3rd input to the XOR gate. So we had done the second signal where we had signal buff is mapped to input 3 after 5 nanoseconds, and it matched. So the result was we had a 10-nanosecond delay, which is what we expected because we have 5 seconds of buffering from the AND gate and the buffer. And then we had the XOR, which was 5 seconds calculating the output signal. So it was the exact same thing as the variable signal, except with a 10-second 10 nanosecond delay, which is what we had coded into it. Yes?
If you're trying to hold a signal like that through the buffer so they don't, so it ends up there at the same time, is there a general rule of thumb? Do you just kind of play with it to see how long it takes? Or is it...
Well, sometimes you want to be able to calculate it. We won't be going too much into depth into this course in terms of design testing and fault tolerance, but sometimes you want to be testing what's known as the critical path, which is the longest path that you're going to possibly calculate in the circuit. And what's going to happen with the critical path is that's where it's going to have the most physical calculations, and you don't want to endure race conditions. And so by using the K-maps to prevent race conditions, you're actually stage by stage trying to ensure it's slowing down. That's where you get that extra area for reducing the race conditions. That's actually causing the signal to slow down so that way at the output, it occurs at the same time. So if you're doing in your final design project, you can actually show that you're using K-maps to reduce the race condition. You're getting a little more area, but the result is that the timing comes out correctly.
That signal from the AND gate reaches the XOR gate before that XOR gate propagates.
Bingo.
Okay.
Exactly right. Anything else? Okay, so this is another example from tri-state buffers and tri-state inverters. Try to go into this a little more detail. I have some Vhdl code down below here. But tri-state inverters and buffers are used for selecting signals, and if it's a buffer, it's going to delay it based on the amount of delay you've coded into the circuit. For example, the tri-state buffer here is going to be the input's going to match the output if the enable signal is equal to 1. Come on. There you go. Now you're cooking with gas. So when the enable signal is equal to 1, you can see that the input matches the output. And then you have a strong unknown value on the output if it's not enabled. So what you can do is, let's say you have an input signal and you're trying to wait for a particular output. You can use the enable signal equal to 0 to not allow this to propagate yet. And it'll hold it until the enable signal becomes 1. And this is very useful. Remember, I was talking about the 5 stages of the MIPS data path: instruction, fetch, instruction, decode, execute, memory, and write back. If you have a value coming out of the ALU, but at the same time you're propagating what's known as an immediate value to try to calculate. So for example, load instruction. What you need to calculate the address and memory that you're going to send the value to in the data memory, as well as the actual value you're putting into the memory. So the ALU calculation for the address is going to take a lot longer than just the value you're getting from the register, which means you need to insert buffers to hold the value that's coming from the registers until you've successfully calculated the address, at which point you can put them both into memory. So this is an example of when you want to use this. And then a tri-state inverter is just the same thing, except you use, when you have a 0 on the input, you're going to get a 1 on the output. When you have a 1 on the input, you get a 0 on the output, provided the enable signal is equal to 1. And to show you, here's the next. What I have next is I actually have some example VHDL code for a tri-state inverter. So what we have here is we have our declared entity. So we have the input and the enable signals and the output signals. So now we have our architecture. If the enable signal is equal to 1, then actually, hold on, this is going to be not DN underscore N. Meaning that's going to invert the signal. Else, the out's going to have the strong Z, and I put it in the comments, we can use Z since we're using the IEEE 1164 standard. So if I wanted to create a tri-state buffer, So you have these problems that you kind of see that the problems are a little redundant. If I wanted to create a tri-state buffer and I had this code, what would I want to do? Yeah, just get rid of the not and change it to tri-state _ buff. And then use a different VHDL code, run the simulation, and you're done.
So that's just one component?
Yeah, so this is now you can use this to have a component in other circuits. Yeah, so if you had like a 32 bit bus, what you could do is you could have 32 tri-state buffers hold the signal, and then with the clock ties into the enable. So if you had a positive edge triggered clock, you could have those all go at the exact same time. It'll propagate the entire bus once the enable signal is equal to 1.
I can't remember if you went over this. How do you put multiple buffers in the whole entity instead of having to do it over and over?
We're going to be going that into a little more detail. Where there's something called vectors, standard input vectors. As we get into multiplexers, that becomes very useful because what's going to happen is you're going to have like 128, 64 inputs where you're comparing 3 or 4 different inputs. You're trying to get a 32-bit output. You can use these vectors to have the 4 inputs and then just map the signals to smaller multiplexers within them. So what we're going to do next is we're going to start out with a 2-to-1 multiplexer and then build up to a 4-to-1 multiplexer and build up to a 16-to-1 multiplexer. But as you can see, after you're getting 16, 32, 64, you don't want to have every single input in there because it can be pretty difficult. So what's going to happen, and I'm going to scroll past this TGO for a split second because I want to give you an allusion to what I'm talking about. So this is what's known as standard logic vector, and it's 15 down to 0. This means you get 16 inputs, and then S is 3 logic inputs. So this is a 16-to-1 mux. So we have 16 inputs, and then we're going to have 4 signals used to control which value you want to pick, and then O is going to be our output value because we're having 1 output signal. But we'll go into more detail there. As the circuits get larger, you're going to eventually want to use vectors and generics. This will cut down on the amount of code you're going to want to do. But also the amount of code that you're will be cut down on is going to be using these components that you're building upon each other. So that way when you get to these really large circuits, you can significantly cut down the amount of code just using component reuse. So the reason why I included multiplexers and I think you guys are or should be familiar with tri-state buffers and the fundamentals of multiplexers. Yes, no? Anybody not? Anything I just said go over your head, please let me know. There will be a question on your exam that will be something to the effect of state the purpose of a tri-state buffer or a tri-state inverter or a multiplexer, which in this case, multiplexers are circuits that use control signals to propagate a selected signal to the output. I'll ask you to draw the logic symbol and a truth table and give me a small snippet of VHDL code. So let's say the problem was state the purpose of a tri-state buffer, draw its logic signal, its truth table, and give me VHDL. This is the only time I'll ask you for VHDL code on an exam. But what I want you to do is I want you to say tri-state buffers are used for selecting signals. You can state that they're maybe used to select a bus. Then you're going to, that's the tri-state inverter. But then you'll draw the logic symbol, the truth table, and then the fourth part will be to drew the tri-state buffer version of this code. And so what I'm looking for on an exam is, can you tell me that you understand that you need to include the IEEE library, you know which library we're using, so you understand that we're using this 1164, and what's the purpose of the 1164 library? You cross it out so you guys can't see the hint that I dropped there.
So we can use the character.
Yeah, remember the topical guide objective. You have all the U, Z, the W, the low and the high values. The multi-value. This is what And it's very important, especially when you're designing an advanced digital system, name of the course. You want to make sure, to get back to, I forget who asked me the question earlier about when we want to make sure that we're using these unknown values. Part of designing an advanced digital system is making sure it actually works under all given inputs and outputs, right? So therefore, understanding that in this particular advanced digital system, not only are you accounting for zeros and ones, but you're also accounting for errors. It means they use the IEEE.standard_logic_1164.all. And .all includes everything from the topical guide objective. From there, if you can draw an entity and an architecture, and here the process should just match your truth table. So the question will either be a tri-state buffer, tri-state inverter, or a 2-to-1 mux. And the reason I ask is because the accreditation board says so. Does anybody have any questions on that before we continue to multiplexers?
So we need to know that table as well.
Yeah, well, okay, so let's go over the truth table where you can actually derive it by understanding the concept. So if I say give you a tri-state buffer, for example, right? And the purpose of the tri-state buffer is to propagate the signal when the enable is 1, right? So without even looking, we can derive the truth table. So I have, what are my 3 values that I want? In, out, and enable, right? So when enable is 0, Z. So you can go enable is 0, and then input is 0 or 1, and both of them are just Z, right? And if it's 1, what is that going to be? Yeah, they're going to match. So now you've derived the truth table by understanding the thing. Same thing with the 2-to-1 multiplexer. The idea behind the multiplexer is we have 2 inputs and 1 output, and we want to select which one it is, right? So you just choose which side it's going to be. So in this case, we have our select signal is 0, and our select signal is 1. And in a minute here, we're going to learn about something called Shannon Expansion, which is it's a theorem that states that every logic circuit can be done about one variable. So if you have 0 or 1 as your choices in the variable, based on that, there's going to be some sort of function that you can decompose it to. So this way, you can actually use this Shannon expansion. Instead of having to go all the way down to the circuit level, you can use multiplexers to then drive smaller circuits to reduce the amount of coding you need to do. But in this case, we can see that our output, 0011, matches A. And for 1, we see that 0101 matches B. So what this circuit is doing is a multiplexer that when S is 0, it's selecting A, and when S is 1, it's selecting B. And that's why the logic symbol here specifically matches A to the 0 here and B to the 1. And that would be something that would be very helpful for you, especially when we get into drawing the data path and MIPS. It'll help you keep track of zeros and ones. So that's how, if you know the logic symbol and you know how it works, deriving the truth table is not difficult. And then from there, if you understand the entity and architecture, it's going to have library IEEE. We're going to have use IEEE standard logic _1164 all, and then entity mux 2-to-1. So all the corrections I made to the document didn't come through. Awesome. Okay, so the mistake that I have here in the go away. There we go. The mistake that's in this document that I thought I'd fix. It says entity 2-to-1 mux. In Vhdl, you cannot instantiate an entity that starts with a number. So in the actual code that I have that's compiled, it's mux 2-to-1. That you can do fine, but it can't start with a number. But our ports are going to be A, B, and S, meaning that we have 2 inputs and 1 output. 2 inputs and a select signal. And O is the output. you can choose whatever you want as long as they match, right? So you can have X, Y, and SEL, and F, as long as it actually works. And so now we have our architecture. This has to match this. So it should say mux 2:1. Let me go down that same page. I'm going to show you the correction. Or if it didn't save, I'll just correct it. If it ever decides to open. There we go. So what this should read is mux 2:1, and it has to match entity at the end here. Mux 2:1, and then architecture, this has to match this, right? For the behavior, and then of mux 2:1. So that is the correct way of doing it. And then inside this, I have a process. Should bring up Xilinx here because I know the code's compiled. But you're gonna have the process you're gonna have all the inputs that you're running inside the process. Begin, end. If S is equal to 0, then output is going to be mapped to A. Otherwise, the output's going to be mapped to B. Same thing with the tri-state buffer. If enable is equal to 1, then it should be not DN. And so this is for the inverter. And if it become a buffer, we would just get rid of not and have it become the tri-state buffer. Does anybody have any other questions on that?
In your process right there.
Yeah.
You have the output.
Yeah. I need to what I wanted to do. Let me get rid of Epic Pen for a second. File, save as. I know this must be riveting for you guys. And the reason I call it section lecture 2 notes print is because I have to print them at the end of this semester to read. Because I have it open. And now I've made the correction to the lecture notes. Yep. And we were at page, I think, 13. Yeah. All right, so now we have our corrected code. Okay, so. Yeah.
You just said earlier you just changed the code and put not in it.
Mm-hmm.
When you put not in it, did that make it so that it would be the inverter? Or?
Yes. Oh. Yeah, for that particular code segment, that was a tri-state inverter. You don't have to write tri-state underscored INV. It's on the exam. Time is short. TSI, TSB works fine as long as they match. And not is what inverts, is what does inversion. It's the primitive variable for inversion in Vhdl. Any other questions? So, as multiplexers get larger, we'll discuss the VHDL stuff at the end, towards the end of class. As multiplexers getting larger, using and or an inverter gates can become much easier than using patch transistor logic to derive functions, right? So now, what we're doing here is that we're using these 3-input AND gates. So you can create a 3-input AND gate and some inverters to create a 4-to-1 multiplexer. Or, instead of having to do all of this, you can use two 2-to-1 multiplexers that control the first signal. So now you have to knock down from 4 to 2. And then what do you want to do with these next 2 signals? Another 2 to 1, correct. And then you have your, so instead of having to design all of this, and you can imagine once we get to a 16 to 1 multiplexer, having to design all these and or gates can be cumbersome. So now you're using these components, 4 to 1 mux using 2 to 1 multiplexers, 16 to 1 mux you can use 4 to 1 muxes, and so forth. So if you were doing, so it's something that happens in a 32-bit NIPS where we have the fixed instruction length, we're trying to choose between two values. So we have two 32-bit values. So what do you think we would do? I want to have a 32-bit value on the output, right? Here's some design. It's not just memorization. Now we're actually designing something. I have two 32-bit input values that I want to multiplex, and I want to choose one of these two 32-bit values. So here's an example of when this would be. If we are doing an R-type instruction, and we have a previous instruction that we've done a load word. So what's going to happen is there's still this existing calculation that we've done. So we want to, I'll get to you, second. So we want to pick between those. And for now, just press the I believe button. At some point, that'll all make sense. But we have two values that we absolutely must choose between. So did you have a?
Yeah, wasn't it like a slant circuitry or something? It was like you could open and close it on the circuit depending on which state you wanted to use.
Mm-hmm. And so basically one way we could do this is is using multiplexers, right?
Right.
So I have two 32-bit values, and I want one of these 32-bit values on the output. So what would I design?
2 to 1.
You have you have a bunch of 2 to 1 muxes to pick. So you have let's call these A and B. So you have A, STD logic vector 31 down to 0, and B 31 down to 0, right? So then you can map 2 to 1 mux 31, 31, 30, 30, 29, 29. And then you have how many?
16 to 1.
Why 16?
No.
No, why did you say 16?
Well, you got 32 bits coming in.
32 bits and another 32 bits, right?
Okay, so yeah.
So
32.
32. There you go. No, I'd rather you guys make the mistakes now than on the exam, right? That's why I wanted you to work through it. I in no way, shape, or form was trying to shame you or anything, just to let you know. So here, this is where we want to start using this standard logic vector that I alluded to earlier in class. And so the purpose of the standard logic vector is for vector of n inputs, we want it to be standard logic vector n minus 1 down to 0. So if we had a 32-bit thing that we just designed, what would my standard vector say? 31 down to 0, correct. So then, let's say if I was doing a 16 to 1 mux here, like this circuit, I would have 15 down to 0 for my inputs. And for the select signal, I would have 3 down to 0. And the reason why is if you see here, I need 1, 2, 3, 4 select signals to do a 16 to 1 mux, right? So I had 1, 2, 3, 4 4 to 1 multiplexers that produce 4 outputs, right? So now we're down from 16 to 4, and we need 2 signals for that, and then we need another 4 to 1 mux, which requires 2 more signals. So that becomes 3 down to 0. And then based on that code, we have our STD logic for our output because we only have one signal that we're propagating. So wouldn't want to do a STD logic vector 0 down to 0. You just want to have, if you're only having one bit, that's what you want. And then from here, so this is an example of a 16 to 1 multiplexer that we have our entity, like we've just designed. And then our architecture, we have a component mux 4 to 1 here, right? with our A, B, C, and D inputs, right? And we have 2 select signals. And then we have our 1 output. And then we have 4 wires. So the 4 wires are going to be the output of 1, 2, 3, 4 muxes. So that's 4 to 1 muxes. They're these outputs, and they all become the input of the last 4 to 1 mux, at which point then we have our output here. So that's why we have these signals. And then, so we have a statutator component, we have our signals, and then based on this, we have our begin and end. So we have, we end up using 5 4 to 1 multiplexers, as we saw in this in the figure. And then this means the 15th or most significant bit of the vector is mapped to A. B is 14, 13, 12. And then we map S3 and S2 to this multiplexer, right? So those are our control signals. And then we do the same thing, 11, 10, 9, and 8. And then we have the same 2 control signals here. Because these 4 multiplexers, if you recall from this drawing before, they're all driven by the same 2 control signals. So this is where using components allows you to significantly reduce the amount of coding. Now you don't have to design every AND gate, every OR gate, every NOR gate. This is where you allow the synthesis tool to take advantage of this for you. And by instead of using variables and using those components, you can still reduce the amount of coding you're doing, but you're not as reliant on the compiler, which means you don't get as much bloat in your final synthesis. And so when you get down to this last multiplexer, which is driving the output, you have wire 3, wire 2, wire 1, and wire 0, which are the mapped outputs here, as you see on the left. Kind of where the code kind of goes over. And then you map S1 and S0, and then you map O to the output. And the reason why that's acceptable code is because the component we previously designed with an O is there, and we designed this one with an O for the 16 to 1 mux. And because we're mapping the component to the actual entity, this is valid code. Yes?
How would we implement our actual input information?
Test benches. So what you're going to do, if you recall from last class, you use a test bench to generate. And what you would do is you would use double quotations, and you could have 0, 0, 0, 0, and then 1, 0, 1, 0, and 1, 1 to map to the vector. And that is actually, I'll get to your question in a second. In the Vhdl Handbook, have you guys had an opportunity to look at the Vhdl Handbook that I posted to Blackboard? For those, I posted a pretty good Vhdl Handbook under contents, reference files, and then there's a Vhdl Handbook there. And so a lot of the things you can look in there and kind of come up with new tricks and things that you see that you might want to use. But I'm trying to teach the Vhdl as we go along with the remainder of the material.
Why is the signal 3 and 2?
Which one? Signal wire 0, wire 1, wire 2, and wire 3?
Oh, okay.
Yes. And so on these type of problems, we're going to be when you're coding in Xilinx, one of the interesting things about the ISE for Xilinx, it ports well into Synopsys, which we finally got installed into the lab. I also posted some description about how to download the ISE file. I got an email from a student who said it was really expensive. Just make sure you follow the steps I use and use the simulation. So that's how you're able to use it for free. Where the cost comes in is when you start needing to buy the permissions and the licensing files for various boards. But you will not be asked to do that. We will provide that for you. You have a question? No? Okay. Yeah, George.
For Mux 4, does it matter like
which wire goes into which input?
Yes, it does. And the reason why it matters is because you want to make sure that and in this case it does because you want to have the values that you're selecting. So let's say you have 0, 0, 1, 0, right? So you want to select, in this case, it'll select input B. Because you have 1, 1, 1, 0, 0, 1, 0, 0, if I remember correctly. But you want to have this specific value that you select and want to select mapped here. So based on these, so if you switch this around, you get S0 mapping to S0 and S1 mapping to S1 here, then you'd switch the inputs. But you want to make, the key thing with a multiplexer is understanding the concept of, based on these select signals, I want this output. Okay. Now, now we're going to address whoever the student who asked me the question about what happens when we get how do we get these values where we have these strong unknown values or these weak unknown values or where we're not quite getting to low and high. This may happen as a result of something called fan in or fan out. And the idea of fan in or fan out is how many wires are coming into your specific block and how many of your particular output are you using to drive other circuits. So fan in is the number of inputs available on a gate. So for example, the fan in on a NAND gate is 2 because we have A and B. And fan out is the number of standard loads driven by a gate output. And I'm going to scroll up just a little bit so you can see the example of fan out. So down here, we have an AND gate that's driving 4 circuits where we have this block logic, right? So that means the fan out is 4. If we haven't designed the signal strong enough, or we don't have a buffer that we can use to regain the signal, one of the things that you can use buffers to is if you have kind of a weak signal, it'll actually, and this is a little outside the course, this is CMOS, but for you to know, if you design a buffer that's driven by the supply voltage and ground, you can actually use it to restore signals. So if you have a signal that's kind of degraded, it's kind of like this, and it goes into the buffer, it'll actually come out properly. And that's how so that's another reason you can use buffers. And how that's done, shameless plug for my course next semester, which by the way is Tuesday. It's going to be Tuesday, Thursday from 11 to 12:15 as you guys requested. So you guys scheduled a course. So. All right, so now we've kind of gotten to this concept of propagation delay and transition time. And so here we have and you guys figure out that this is the fan out here is 4. And if you're driving too much, what's going to happen is it's going to actually degrade the signals. If you have your fan out is too much. So you want to reduce fan out. And when you're actually using the board synthesis, which we'll get into later, in the course, in section 3, we are going to describe how the compiler will not allow you to have too much fan into one particular gate.
Is there anything that prevents too much fan out?
Oh yes, fan in and fan out. By basically, it'll do calculations based on a predictive technology that's used within the embedded system compiler. And based on that, it'll actually see whether or not you can actually successfully drive the gate. So this is design automation, which is another kind of a whole field of testing fault tolerance and design automation. There's people who this is their job. Like this is what they do for a living. And it's important because you want to be able to, you don't want the circuit to fail, especially in a car that's monitoring for the airbag or the brakes. You want to make sure that it works at all times. Yeah.
Do those buffers not allow you to have more fan out?
The buffer will typically have one input and one output. So you want to have a fan in of one and a fan out of one. And so I included a diagram in the notes to describe and further here about propagation delay and transition time. So propagation delay is the time required for a change in the value of a signal to propagate from an input to an output. So let's say you have an inverter or a tri-state inverter, right? So we have 0, and so we have this kind of output Z value. And then the enable signal becomes 1. The propagation delay is the amount of time from when the enable signal turns 1 to getting the output on the tri-state inverter. So whatever that amount of time is. And here, this chart here actually shows, so to transition from low to high, TLH min, and TLH max, is this circuit. So these are all doing the same thing over a given amount of time. So the stimulus occurs here, and then it takes a certain amount of time for each of them to change, right? And then the propagation, the transition time, so if you're looking at this chart, propagation delay is here to here, and transition time is the amount of time it takes to get from a certain value. So if you're let's say you're doing the same thing where you have 1 and 1, and you have where if you haven't properly coded in, it could possibly change. What could actually, remember we were talking about if you have that delay where it's shown, we showed it in Vhdl, we have this slight blip in time. So if we're running at a high frequency, I think this is what you were talking about a couple of classes ago, we can have an instance where if we don't properly ensure a race condition, it'll go down a little bit, but then it'll actually, now it has the right value, so it'll come back up. And that's when we start getting the correct calculation. So that's an example of how the transition time affects the synthesis of a digital circuit. And the propagation delay, then transition time is specifically going from a 0 to 1. Does that make sense?
Are there standards associated with transition times?
Yes. Yes. You're going to be the idea is what happens if this is the implementation technology. So this is going down to SSI and even lower. So if we're going back to our wire chart where we're dealing with polygons, at that level, you're dealing with specific voltages. So if you're dealing with 25 micrometer, or you want to have, it's going to be 3.3 volts, but if you're doing like 22 nanometer, like we're using in the Intel Ivory Bridge, you're going to be using like 0.9 volts. So based on that, you want to be able to have, you're going to have certain values where it's going to be an acceptable voltage. So we're talking about TI and TL. If you're between here and here, this is an acceptable 1 and this is an acceptable 0. And so here you're going to get your Z values, right? And if it's strong there. And so if it's weak, this is where, so let's say this is the acceptable value. This is where H is. And L is here, but the acceptable value of L is kind of below that, right? So L is we haven't quite reached the acceptable standard. H is we haven't reached the acceptable standard for a 1. Okay. 10:30. And so to answer your question even further, we define the maximum amount of fan out here as the maximum fan out that can be driven by a gate is the number of standard loads the gate can drive without exceeding maximum transition time. And now we'll go into cost here in a minute. So if we have a certain amount of time, we say it has to be able to change from here to here in order to properly represent the signal from a 0 to a 1 or a 1 to 0 like this. If this is our maximum transition time, and we have an example where it's going to take too long, and so let's say that this was a fan out of 4 and this was a fan out of 5, that means that our maximum fan out is going to be 4. So with everything, there's pros and cons. You're able to reduce race conditions. we want to make sure that we hit our, we don't want to go over the maximum fan out, which means we may have to have a redundant signal to drive both circuits, right? But those come with a cost. In this case, our cost is defined as a measure of the contribution by the gate to the cost of the integrated circuit. So we're going to have three different metrics. Here we have a literal cost, which is the number of literal appearances in a Boolean expression corresponding to the logic circuit diagram. So in that little combinational circuit, we had A and B or C, right? So this actually corresponds to the actual literal appearances, meaning A, B, C. So that literal cost becomes 3. Next, we have our gate input costs, and we're going to go over an example question of how to calculate these here in a minute. Our gate input cost is the number of inputs to the gates in the implementation, corresponding exactly to the given equation or equations. And then, so we have G is gates, and GN is when we count inverters. So in this case, for A and B or C, our G count is going to be 2 because we have one gate for and then we have a second gate for or. And our GN is going to be 0 because we don't have any signals inverted. So if we had not A and B or not C, the difference would be our GN value here would be 2 because we have 2 inverters inverting those signals. So we have cost, literal cost, and gate input costs. Does anybody have any questions on that before we go to the example question?
Any G inverters, not kind of G inverters, kind of.
GN means gate. Well, I'll show you in the example question. But basically, that means that we have the G is just before you take into effect that you have to invert certain inputs. So this example here, example question 2.1, we have 2 logically equivalent functions. One F equals A and B and C, or not A and not B and not C. And the second function is F equals A or not C, B not or C, A not or B. These are logically equivalent. And now we have to calculate the cost of each function and show which one may be implemented as a lower cost. So engineer 1 says, let's do it like this. Engineer 2 says, let's do it like function 2. Your job is to figure out which one has the lower cost. So the solution, we're going to use the literals. The literal is each listed input. So I have the literals in this function here. I'll scroll down just a little bit so you can actually see both functions. The literals are listed as the red dots, meaning that A, B, C, A naught, B naught, C naught, each input is a literal. So we have the literal gate cost, that's what we're talking about there. So the literal is 6. So if I were to ask this as part of an exam question, I would expect you to say L is equal to 6. Here, what are my gates? My gates are represented by the green dots, meaning that I require 2 3 input AND gates to have our circuit. That is G. G naught is taking into account the number of inverters. So in this case, I'm going to scroll up a little bit more for the people in the back. I'll get to your question in a second. These are represented by the black dots. So we have not A, not B, and not C are inverted. So that becomes our GN value. So literals, 1, 2, 3, 4, 5, 6, L is 6. Gates, we require 2 gates. And additionally, we need 3 inverters. And those are the black dots. So it becomes the total cost of the circuit becomes 6 plus 2 plus 3, which is 11. You have a question?
Do we not need to have an OR gate for?
Yeah, 1, 2.
No OR gate.
Yeah, well, it's going to be a combination. That's the calculation of the gates. I'm gonna do it. I took this from the book.
So there's an order.
No. I took this from the book. This is it from an answer key. Why did I leave out the OR gate? Why did I leave out the OR gate?
Because in the circuit also there are like 3 green dots in the circuit level.
Probably should be 3. Because down here I have the circuit representation. 1, 2. Should be.
It calls them a unique gate up there, so since A, B, C, and A not, B not, C not are each unique.
Yeah, because here's the final circuit. Yeah, because it requires a 3rd gate here. So it's probably, and this requires a 4th gate. 1, 2, 3. And then you can implement those A or 3 OR gates. All right, well, since it requires 3 gates, we'll do 3 gates there. And this will require 4. Yeah, we can change it. As long as we're consistent, right? So now we have 1, 2. Let me put a green dot there since I said they're in green. Right? And then we'll put the 4th green dot there in the second part.
So we're just gonna have one.
Yeah. I'll look into why that is. I know I took that from an answer key. We'll just keep that consistent. Right now, how it doesn't have any impact on the problem. So this becomes 12. And then for the second start gate, we have 1, 2, 3, 4, 5, 6. So we have 6 literals again. We have 1, 2, 3, and then 4 for the 3 input AND gate to compare all of these on the output. And then here we have 1, 2, 3 inverters. So now the cost becomes 13.
Is there ever a time you'd want to choose something with a
Higher cost?
higher cost?
Yes. Bingo. Race conditions. And so I think that might actually be my next example of. Oh no, it's down a couple more example questions. So, yeah, that's the perfect example of when you want a higher cost.
Like always mean like faster, or does sometimes does lower cost mean like faster? Or
Lower cost always means faster. Remember the 4 design principles? Smaller is faster. Smaller is always faster because it's going to go through fewer transistors, fewer gates to get to the output. But faster isn't necessarily what you want because you want to prevent those race conditions. So to bring up the again. There. And I will look into why that is. I know I took that from an answer key, though, so there's probably something I'm forgetting. Partially is that here we have a 2-input OR gate, and then we have a 3-input AND gate on the output, and there can be issues about combining gates. But that's a theory. Let me save that. Okay, so combining concepts. So we're going to use a Karnaugh map, design a 2-to-1 multiplexer, and then calculate the total cost of the 2-to-1 mux. So we have our truth table here. And then we have our selects 0 and 1, just like we had in the previous. So then, using that, we have our Karnaugh map. And we get our put here. And so our result becomes, our function becomes select not A or select B, which is what we expected. So the Karnaugh map matches our expectation. And then our literal cost becomes, I'm going to change that to 3 for the time being. Literal cost becomes 4 because it's 1, 2, 3, 4. Our gate cost becomes 1, 2, 3. And our inverter cost is 1 because we have this initial S. Let me delete everything. So you see the S naught. And so how that matches is we have AND gate, OR gate, inverter. Then I really got to look into that because that should be 8.
Yeah, you got gate cost.
Yeah, I when I was making the notes, I remember thinking that was weird, but I stuck with it.
Would there be a risk condition at the 1, 1, and 1?
If you don't properly buffer it, yeah. So that becomes an issue. Sometimes you can have the inverter signal delay, a very small delay.
Mm-hmm.
So what you could do is you could either have a buffer here, and you would actually delay it like in an AND, and then for example in an AND gate. One way you could do this is to actually you have an NAND gate and inverter, and have the inverter serve as the buffer. So that's how you do it at the CMOS level. Now we're almost out of time, so I just want to answer you asked the question about cost versus race conditions, and recall from the previous example from class, we had this K-map that we used to calculate a function, and then we expanded the P subcubes in order to actually get to eliminate the race condition, right? So before, and then we updated the function based on our result, right? So now the initial circuit had a cost of 7, but then when we update everything to have the rate to account for the race conditions, the cost actually increases to 13. But it's slowing down to make sure that everything changes at the exact same time. So that's the trade-off between cost and speed. Okay, so we did 2.7 through. I'll stop here. So our homework assignment is 2.7 through top.
TGO's not a good number.
Yeah, they're all messed up.
They are.
Yeah.
You're all plus 2.
I got like 2.
Okay. I'll email out the assignment then. And there should be example question 2.1. I'll email it out.
There's the 2 TGOs that wanted pre-design, and I think it was 2.10 that it was labeled as.